So how do we actually make decisions together? I mean, think about it. Whether it's like a group picking an ice cream flavor or something really big like, millions of people electing leaders, the basic idea seems simple, right?
Yeah, you just count the votes, majority wins, that's it.
Exactly. Job done. It feels like it should be straightforward, a clear way to get the outcome the group wants.
Well, that simple picture assumes our collective preferences sort of behave nicely, logically. If you prefer A to B and B to C.
Then you prefer A to C.
Right. That's called transitivity. We expect that in, like, rational individual choices. And we kind of hope our group choices work that way too, cleanly, logically.
Okay, but here's where it gets, well, messy and really fascinating. The sources we're digging into today, looking at ideas from books like Simplexity, Critical Mass, they show that this simple transitive logic, it often breaks down, especially when you have more than just two options.
Yeah, imagine trying to get a whole room to agree on one ice cream flavor when there are like a dozen choices. Preferences can get tangled up really fast.
And this isn't just theory, is it? The sources point to actual examples.
Yeah, they bring up the 1968 U.S. presidential election. You had Nixon, Humphrey, and Wallace. A three-way race.
Right, and different groups, different states, had pretty different preferences among those three.
Exactly. The sources look at reported preferences in places like Arizona, Arkansas, Pennsylvania, and when you compare the candidates head-to-head based on that data, well, the analysis showed, okay, Nixon versus Humphrey, Nixon wins.
Okay.
Humphrey versus Wallace, Humphrey wins.
So Nixon beats Humphrey, Humphrey beats Wallace. Logic says Nixon should definitely beat Wallace then, right?
That's what you'd absolutely expect. But here's the paradox the source highlights. Using that same preference data, if you put Nixon directly against Wallace,
Wallace wins.
Wallace wins against Nixon. The simple ABC chain just breaks.
Whoa. So the group preference actually cycles. Nixon over Humphrey, Humphrey over Wallace, but then Wallace back over Nixon. That feels wrong somehow.
It's totally counterintuitive. But the main point here is that this kind of cycle, this non-transitive group preference, isn't just some weird math quirk. It can actually happen in a democracy with diverse views.
Okay, so what does that actually mean then? If our collective preferences can cycle like that, what are the implications?
Well, the sources really get into this. It raises some big questions. First, it suggests election results can be kind of unstable.
Oh, so?
Like, the winner might depend a lot on who exactly is running, or even the specific way you count the votes. Which makes you wonder about, fairness.
Okay, fairness is one thing. What else?
The other thing is, maybe even more fundamental, is efficiency. It means the final outcome of a vote might not actually be the option most people would prefer if, say, the choices were presented differently.
So we might not even be picking the best option according to the group's overall wishes.
Potentially, yeah. It complicates that whole idea.
This sounds like a pretty deep, almost mathematical flaw in the whole voting process itself. Has this been, formally studied?
Oh, absolutely. This problem was really nailed down by Kenneth Arrow, the Nobel laureate economist from Stanford. His work is foundational here.
Arrow's impossibility theorem? I've heard of that. What exactly did he prove was impossible?
Right. So Arrow basically asked, can any voting system reliably turn diverse individual preferences into a single coherent group preference while satisfying just a few reasonable conditions?
Conditions less.
Like, basic fairness to all candidates, being responsive to what voters actually want, making sure the outcome isn't dictated by some irrelevant option nobody likes, things that seem obvious.
Okay, seems reasonable.
Yeah. But his theorem proved it's mathematically impossible for any democratic voting system, any system that isn't a dictatorship, to meet all of those reasonable criteria at the same time, especially when voters have different rankings.
Wait, impossible. So you're saying you can't have a system that's simultaneously fair, responsive, and logically consistent if it's not a dictatorship?
That was Arrow's big and kind of unsettling conclusion. He argued the only way, theoretically, to guarantee a collective choice that satisfies all those desirable logical conditions without any conflict is, well, if one person decides for everyone.
A dictator.
Essentially.
Yeah.
Any other system, any democratic system, is going to fall short on at least one of those criteria when faced with enough diversity and preferences. It's like a fundamental limit.
Wow. Okay. So that's a huge insight from that sort of mathematical individual preference perspective. But the sources we're looking at also bring in a totally different angle, right? The complexity view.
Exactly. The complexity perspective says, hold on, maybe voters aren't just isolated individuals with fixed preferences that we add up. In the real world, people talk. They influence each other.
Choices aren't made in a vacuum.
Not at all. And the source material highlights this really well, particularly discussing analysis and critical mass by physicist Raimundo Filho. He looked at huge amounts of data from the 1998 Brazilian election.
How huge are we talking?
Over 100 million voters electing multiple officials, a massive data set.
Okay. And what did he find looking at all those votes?
The really striking thing was the distribution of votes. It didn't follow a standard pattern like a bell curve, which you might expect if everyone was choosing independently.
What did it look like instead?
It followed a classic power law pattern.
A power law.
Mm-hmm.
What does that mean in this context? Like, what does that pattern tell us?
A power law basically means you have a few things that are vastly bigger or more frequent than most others. Think about, like, city sizes, a few huge metropolises, tons of small towns, or wealth, a few billionaires, lots of people with much less.
Okay.
So in the election data, it meant a few candidates got a huge number of votes, way more than you'd expect by chance, while most candidates got very few. It's a very skewed distribution.
And why is that significant? What does the power law suggest?
It strongly suggests that voters weren't acting independently. That pattern is often a sign of underlying interactions, of influence spreading through a network. People's choices were connected.
So not just isolated decisions, but decisions influenced by
Right.
friends, media, general buzz.
Exactly. It could be conversations, seeing what neighbors do, media influence, just the general spread of ideas, behaviors, even styles. Richard Dawkins coined the term memes for this kind of cultural transmission, right?
Right. Units of cultural information spreading.
And this view changes the whole picture from Arrow's model. An election isn't just summing up fixed votes anymore. It's more like watching a dynamic, interacting system unfold.
Which implies?
Well, a key feature of these complex systems is sensitivity. Small initial changes, maybe a rumor, a key endorsement, a particular news story, could potentially ripple through the network and lead to vastly different outcomes than you might otherwise expect. It challenges that idea of purely independent, free choice driving the result.
That's a very different way of thinking about it.
Yeah.
Okay, let's broaden this out from just elections. How does this complexity idea apply to collective decisions more generally? The sources talk about a computer simulation.
Yeah, the one by Joshua Epstein at Brookings. It's discussed in a paper called Learning to be Thoughtless, which is a great title.
Intriguing. What was the setup?
Super simple model, really. He had 190 little agents, like simulated people, arranged in a circle. They had to choose between two colors, yellow or blue. Think of them like political parties or just competing choices.
Okay, yellow or blue. And initially,
They were just assigned a color randomly. Total chaos, mix of yellow and blue.
and how did they decide which color to be? What was the rule?
The rule was designed to be simple, based on minimizing effort to agree locally. Each agent would look at a small sample of its neighbors, see which color was the majority in that little group, and adopt that color. Then, crucially, they'd adjust their sample size, find the smallest group of neighbors needed to confirm that local majority, and then just stick with that color and group. They basically stop checking once they find local consensus easily.
Sort of modeling how people might follow the crowd without thinking too hard once things seem settled nearby.
Exactly. Minimal cognitive effort to align.
So what happened in the simulation when it ran like that, without any disturbances?
It was pretty amazing. Starting from that random yellow-blue mess, the system quickly self-organized, agents started matching their neighbors,
Yeah.
and very soon, distinct, stable blocks of solid yellow and solid blue emerged, like little countries forming. The agents inside these blocks settled down, stopped sampling, and the overall pattern became really stable, really fixed. They learned to be thoughtless within their group, as the title suggested.
Chaos to order.
Yeah.
But then they threw a wrench in the works, right? Introduced some noise.
Oh, yeah, exactly. They added a random element. Like, imagine a sudden news event, some external shock, or just a random chance an agent might reconsider its color choice, forcing it to look around again.
Like real life, things get disrupted. What happened then?
When the noise hit, the system went chaotic again for a bit. Agents were forced to resample, neighbors might have changed, decisions were up in the air. But the really striking part was what happened next.
It settled down again.
It restabilized very quickly back into clear yellow and blue regions. By UT, often the new stable pattern looked completely different from the one before the noise. The sizes and locations of the yellow and blue blocks could be totally rearranged.
Wow. So a shock leads to chaos, then a new, different kind of order emerges rapidly. What are the big takeaways from that? The source highlights a couple of key insights, I think.
Yeah, two really interesting ones. The first is about how, well, maybe fickle people can be collectively. Agents that were solidly, stably yellow before the shock could easily end up being solidly, stably blue after the shock in the new configuration.
So it suggests many people might just go along with the prevailing current, the mainstream, almost mindlessly adopting whatever the new consensus is.
That's what the simulation implies, yeah. Conforming to the new local majority without necessarily a deep reevaluation.
Okay, that's one insight. And the second one, you said it felt particularly powerful.
It really is. It's about the influence of the few. Remember how agents in the middle of the big yellow or blue blocks stopped thinking or sampling?
Yeah, because everyone around them was the same.
Right. But at the boundaries, the edges between yellow and blue regions, you had a minority of agents who still had mixed neighbors. They were the ones still actively sampling, still making decisions.
The ones on the fence, so to speak.
Exactly. And when the noise hit and everything went chaotic, the simulation suggested it was often the choices made by these few agents at the boundaries during that chaotic phase that ended up determining the shape and layout of the entire new stable system.
So the fate of the whole system, the new pattern of yellow and blue, was disproportionately influenced by this small group of boundary thinkers.
That's the implication. Their decisions, made when things were in flux, had an outsized impact on the final outcome for everyone.
That is powerful. And there was another example reinforcing this idea, something about standing ovations.
Yeah, seems like a jump, but the principle connects. It's a study by Scott Page at the University of Michigan from 2004. He simulated when a theater audience gives a standing ovation.
Okay, what drives that? The quality of the show, how big the audience is.
You'd think so. But Page found those factors were often less important than something else entirely.
Which was?
The actions of the people in the very first row.
Just the first row. Why them specifically?
Because everyone else can see them clearly, they act as really visible social signalers. Page's model showed that sometimes all it took was about 10 people in that first row, standing up to trigger a cascade, getting the entire audience to its feet.
Even if the show wasn't that great.
Potentially, yeah. Their visible action was the critical trigger.
So those first row social signalers, they sound an awful lot like the minority boundary agents in Epstein's color simulation.
It's the exact same kind of idea, isn't it? A small, strategically positioned or highly visible group whose active choices at a key moment can unleash a much larger collective behavior shift.
Fascinating. Both studies point to the same dynamic. Change being driven not necessarily by the mass, but by a critical few.
It really brings together these different threads.
So let's tie this all back. We started with voting seeming simple, then saw the logical paradoxes.
Yeah, Arrow's theorem showing the inherent difficulties.
Then we shifted to the complexity view, the power laws suggesting interaction.
Voters influencing each other, not acting alone.
And these simulations suggesting how collective opinion or behavior can form, stabilize, and then rapidly shift based on noise and the actions of a few key individuals.
Right. It paints a much more dynamic and maybe less predictable picture of collective choice.
So coming back to that old Bismarck quote, maybe politics really isn't a precise science. It's more complex.
Or at least it behaves like a complex system. And maybe you don't need to get too hung up on the pure mathematical flaws of voting systems or feel like power laws mean everything is predetermined.
What's the really interesting takeaway then from this whole deep dive?
For me, the most compelling thing weaving through these sources from Arrow to Epstein to Page is this idea about how change happens. A really significant shift, maybe even a revolution in thinking or behavior, might not need a majority to get started.
It just needs that initial spark.
Yeah, maybe just a small catalyst, a few key actors, those boundary agents or social signalers, making a move. Meanwhile,
most people might be like the audience members in the back rows, or the agents deep inside the yellow or blue blocks.
kind of just waiting to see which way the wind blows and then aligning with the new pattern once it starts to emerge and solidify. Perhaps, as Epstein's title hints, somewhat thoughtlessly.
Which really leaves you thinking, doesn't it?
Yeah.
What is this insight about the outsized power of a relatively small number of boundary thinkers or social signalers to trigger large-scale shifts? What does that mean for you?
Yeah, how does that change how you think about influence or change in your own community or work or just the world around you?
Definitely something to chew on.